Hello and welcome to part 3 of Unit 2. In this part, we're going to introduce the concept of acceleration. By definition, in physics, acceleration is a change in an object's velocity in a time interval. Because acceleration is based upon velocity, and velocity is a vector, acceleration is as well, so it will have a direction associated with it. Just as we saw with velocity, we also have two definitions for acceleration. We can have the average acceleration, which is calculated by the change in the velocity over time, or we can have an instantaneous acceleration, in which case we are taking a derivative of the velocity with respect to time. Okay. Because the instantaneous acceleration is found by a derivative, remember that this means if I have a graph of velocity versus time, I can find the instantaneous acceleration at any point along this graph by calculating the slope of the tangent line to the curve. Let's consider an example where we calculate average acceleration. In this case, our initial velocity is 0. We're in units of kilometers per hour. And 6.2 seconds later, we are moving at 95 kilometers per hour. Because acceleration is a vector, we need to define a coordinate system. It makes sense in this case to let our positive direction be in the direction of the final velocity. The other thing that helps when doing this problem is to do the unit conversion first. Oops, I forgot the 5. There we go. If you do not do the unit conversion first, the units kind of get murky, if you will. It's still doable, but it is much easier to do it if you do them first. So to convert units here, I need to multiply by 1,000 and divide by 3,600. And that results in 26.39 meters per second. I can now calculate my acceleration by taking the change in velocity over the time interval. My change in velocity is my final velocity, which is in my positive direction, so I'm going to stick a positive sign there, minus my initial velocity. If it's 0 kilometers per hour, that's 0 meters per second as well, and dividing by the time interval, which is 6.2 seconds, and that results in acceleration of positive 4.26 meters per second squared. If I asked you for the magnitude of the acceleration, you would tell me 4.26 meters per second squared, because again, a magnitude does not have a sign associated with it. Let's think about what happens to a car if we change the direction of the acceleration on it. If we have a car traveling to the west, typically on a compass, west is to the left, so I'm going to go with it. So here is our car traveling at 55 miles per hour to the west. And the acceleration is in the same direction. That means that the sign of the acceleration and the sign of my initial velocity have to be the same because they're both pointing to the west. If you think about what that means, in order to get them to have the same sign, that means that the velocity will increase. The car will speed up. Okay? So to give you an example, if I'm currently going 55 miles per hour and sometime later I'm going 65 miles per hour, then when I come up here and subtract 65 miles per hour minus 55 miles per hour, divided by however long that took, which is not necessary in this case, we get an acceleration that is a positive number, just as I assumed my velocities were when I plugged them in. Okay. On the other hand, if my car is traveling 55 miles per hour west and my acceleration is to the east, now if we think about signs, that means that I would have to be slowing down. And I can again illustrate that by plugging in quick numbers. So my final velocity now is 45 miles per hour. My initial was 55 miles per hour. Notice I plugged this in with a positive sign. That means west is positive, or an implied positive sign. And we can see that this is negative 10 miles per hour. So that would mean it is in the opposite direction of the assumed positive west direction, or my acceleration is east. And indeed, we lost some speed there, so we slowed down. Okay. This last one you can't see as easily by just plugging in numbers. But if the velocity is to the west and the acceleration is to the north, what's that going to do? Well, it's going to cause the velocity to have a piece to it that now points to the north. So it has now changed the direction of the velocity. So this particular scenario will result in the car turning. In fact, if the acceleration and the velocity are always perpendicular to each other, then you will turn without changing the magnitude of the velocity. So you will move in a circle at constant speed. One problem that students have with physics comes from language, because the way we use the language in physics is different from how the language is used in everyday life. Acceleration is a prime example of this. In everyday life, we say we're accelerating, and that means our velocity is increasing, we're speeding up. If I say I'm decelerating, that means I'm slowing down in everyday life. And if I want to do something else like turn, I say I'm turning, I'm changing direction. In physics, we have one word that encompasses all three scenarios: acceleration. Therefore, I will not use the word decelerate. Okay? Decelerate in everyday life means to slow down. That's encompassed by the word accelerate by the physics definition. So I won't use it. That being said, your book does use it, and you may see it in the homework. If you do happen to see it, what you need to keep in mind is decelerate means slowing down, and it means acceleration and velocity are in opposite directions. So you need to put in the signs for those two quantities correctly. Continuing along, we're now going to think about how we can get the same motion by changing around the coordinate system. So for numbers 1 and 2, or the first two scenarios here, we're going to work with up as positive. And for the last two scenarios, we're going to work with down as positive and then analyze the same motions. Okay. So In the first two, we're going to let up be positive. For the first one, the velocity is upward. I throw a ball straight upward. When I throw a ball straight upward, I know that eventually it slows down and turns around and comes back down. So velocity is going to be decreasing. That means the acceleration has to be downward. So velocity will be positive and acceleration will be negative. For scenario 2, the ball is coming down. It's being dropped straight downward. That means that the velocity will be negative. But again, I know what happens when I drop a ball. As it falls, it gains velocity. Therefore, the acceleration must be in the same direction, which means it is also negative. Let's now rotate our coordinate system so that we have a down positive coordinate system. We go back to ball is thrown straight upward. So velocity is upward. This means our velocity is now negative because it's upward in a down positive coordinate system. But it is going to slow down as it travels. That means our acceleration is positive. And lastly, the ball is dropped again. So velocity will be positive because it's downward in a down positive coordinate system. And as it falls, it will speed up. Therefore, acceleration has to be downward as well. And down is positive. Here you can see that regardless of how I defined the coordinate system, the relationship between the signs of my vector quantities stays the same. When you work these problems, you need to define a coordinate system. And as long as you are self-consistent with the coordinate system, the math will work out to give you the answer within that coordinate system. It may differ from somebody who chose a different coordinate system, but you should be able to reconcile the differences by comparing your two coordinate systems. And if you can't, someone has done something wrong. Lastly, I want to think about acceleration and velocity just a little bit further. The first question is, can an object have a zero instantaneous velocity and a non-zero acceleration? Well, if I think about acceleration as the slope of the velocity over time graph, I can imagine a point in time where my velocity equals 0, but the slope of the line going through that point is not 0. Therefore, the answer here is yes. Can your velocity be 0 and your acceleration non-zero? Yes. A good example of when this happens is a ball at the top of the motion. If you think about a ball being thrown upward, it moves up, slowing all the way. When it hits the tippy top, it stops instantaneously and then turns around and comes back down. At that point at the top, it's not moving, but it is changing direction. It is going from moving up to moving down. For the second question, can an object have a zero acceleration and a non-zero instantaneous velocity? The answer here also is yes. To get an acceleration of 0, I need to have a slope of 0. Well, a slope of 0 is a flat line. So here my acceleration is 0, but my velocity is non-zero. It's some number. Might be positive, might be negative. So the answer here is yes. And the key to it is you need to be moving at a constant velocity. This concludes this part of Unit 2.